appetite. Let's unpack this. Today, we're diving deep into a really fascinating world where quantum computing meets AI, specifically quantum circuit optimization. Our source material today, it's from a pretty comprehensive GitHub repository, a project designed not just to generate quantum circuit data, but then, and this is the kicker, optimize those circuits using, well, a very well-known AI. So our mission really is to pull out the key insights. How are these complex circuits made, simulated, and crucially, how are they being optimized? There's a surprisingly elegant synergy here.
Yeah, what's truly fascinating, I think, is how this project gives us such a clear, practical example. You see cutting-edge AI being directly applied to, frankly, one of the stickiest problems in quantum computing.
Making them efficient, right?
Exactly, making these circuits efficient and precise. It's all about tackling those inherent inefficiencies in quantum systems.
And that focus on efficiency, it really underscores why getting the data right at the start is so critical. Before optimizing, you need the raw materials.
Yeah.
And this project's data generation module, it seems quite sophisticated. It's mostly built using Cirq.
That's right, Cirq, Google's open source quantum framework.
Makes sense. So how does it actually generate this data?
Well, it looks like it intelligently creates these random quantum circuits. It varies the number of qubits, the complexity, controls the number of non-measurement gates,
Standard practice, but necessary.
and it uses a foundational set of quantum gates. Things like the single qubit gates, XYZ,
Are
Hadamard,
workhorses.
yeah. And then the crucial two-qubit gates like CNOT and CZ for entanglement and, well, more complex stuff.
Right, you need those interactions. But it's also flexible. You can plug in a custom gate set, too, which seems important for, research.
Definitely. You don't want to be locked into just one set.
And every operation, whether it's a gate or a measurement, it's meticulously recorded, structured format.
Capturing the blueprint.
Exactly. It captures the type like poly X or measurement gate, which qubits it hits, the exponent, a precise blueprint, as you said.
Okay, so generating the circuits is one thing. What about simulating them?
Ah, right. It handles that too. Robust simulation capabilities. You can simulate with noise-realistic noise.
Which is key, because real quantum computers are noisy.
Totally. It uses models like depolarization, bit flips, phase flips, gives you measurement results that reflect sort of real-world performance.
Okay.
But it also offers noiseless simulations, state vector simulations, which are vital for understanding the circuit's ideal behavior, the underlying probabilities.
So you get both pictures, the ideal and the messy reality.
Precisely. And one more thing before the AI jumps in. It applies a baseline optimization, just using Cirq's built-in tools.
Ah, like a vanity check.
Or a benchmark. Yeah, a classical benchmark for efficiency. Then all this info, the raw circuit string, the structured operations, gate counts, simulation results, noisy and noiseless, and that Cirq-optimized version, it all gets saved neatly into dataset files, usually JSON lines.
Okay, hold on. This raises an important question for me. Why go to the trouble of having both noisy and noiseless simulations and that baseline classical optimization right there in the dataset generation? Especially if you know you're going to throw like a powerful AI at it later.
Yeah.
What's the strategic thinking?
That's a great point. My first instinct might be, well, just get the clean, noiseless data. But it sounds like there's more to it. Why is that multi-layered approach so critical?
Exactly.
Yeah.
And the reason is actually quite simple, but powerful. It gives you a much more complete picture of how that circuit might perform in the real world.
Because of the noise.
Because of the noise, yes. Without that noisy simulation, you're only looking at an ideal scenario, which often isn't very real.
Right.
And just as crucially, that classical optimization,
Yeah.
that's your baseline, your comparison point.
Right.
Without it, how do you know if Gemini's optimized circuit is actually better?
Right.
It's different. You need that objective measurement.
That makes perfect sense. Okay, so that sets the stage beautifully. We have this solid foundation of quantum circuit data, realistic simulations, a benchmark. Now the next phase. This is where I think the project really takes a leap. Applying cutting-edge AI, specifically Google's Gemini, to this, let's face it, really tough problem of quantum circuit optimization.
Right, using the Gemini 2.5 Pro model.
Yeah, and when I first saw they were using Gemini, I admit my eyebrows went up a little. It feels bold. But the technique they're using is, well, surprisingly elegant. It's in-context learning. Think of it like teaching a really smart apprentice just by showing them a couple of perfect examples instead of handing them a giant textbook.
Less brute force training, more targeted demonstration.
Exactly. So how does it actually work? You give this system an unoptimized circuit, Maybe, a simple string like H0, CNT01, H0.
Okay.
Then the system builds a prompt for Gemini.
Yeah.
But it's not just your circuit. It strategically includes these in-context examples, pairs of unoptimized and optimized circuits.
The showing the apprentice part.
Precisely. And these examples are critical. They're explicitly defined in the project. Like one pair shows H0 CNOT01, H01, H0 CNOT01.
Right. The classic CNOTH equals CNOT identity, essentially.
Yeah,
Yeah.
it demonstrates that simplification. Another example is X0, X0, Y1, Y1 shows that two X gates cancel out.
Basic but fundamental optimization rules.
Exactly. So these pairs get prepended to your input circuit in the prompt. It's structured like optimize these circuits, unoptimize. Example 1, optimize your circuit, optimize, and Gemini just completes it.
It learns the pattern from those few examples.
Seems so. And access, by the way, is through an API key, handled securely, loaded from a specific file in your home directory, .ap-gemini. Very specific format, just the key.
Good practice. So connecting this to the bigger picture, what this project really demonstrates is, well, maybe a bit of a paradigm shift.
How so?
Well, think about it. Traditionally, fine-tuning a huge AI model for a specialized task like this could take months, massive data sets, huge compute.
Right, a major undertaking.
But here, they're leveraging this in-context learning, essentially teaching Gemini complex quantum optimization just by showing it a handful of good examples within the prompt itself.
It's like a shortcut.
It's more than a shortcut, I think. It's potentially a blueprint for rapid AI deployment in these really niche, specialized scientific areas. It means general-purpose models like Gemini can become incredibly agile tools.
Wow, that's incredibly insightful. Adapting quickly without massive retraining.
Exactly.
So, okay, where does this go next? What does this mean for the future of this quantum AI synergy? The project's ongoing, right?
Yeah, it's definitely presented as an active area.
And the sources point to some exciting future directions. On the data generation side, they're talking about generating much larger, more complex circuits, exploring different structures, different gate sets.
Failing at the foundation.
Yep. And then on the AI side, with the Gemini optimization, there's a clear roadmap laid out. They're planning more advanced prompt engineering, trying to squeeze even better optimizations out of Gemini.
Fine-tuning the teaching method.
Right, and exploring different generation strategies, seeing if Gemini can produce maybe multiple different optimized circuits, not just one.
Interesting. Options are good.
And then automated evaluation. This seems crucial. Figuring out how to automatically measure how good Gemini's optimizations are, comparing gate count, circuit depth, maybe simulation fidelity.
Closing the loop.
Yeah.
Automating the quality check.
Exactly. They're also looking into reinforcement learning approaches, maybe even using Gemini itself to provide feedback for more optimization.
Ooh, getting meta there. Using the AI to guide its own learning.
Yeah, and even incorporating error mitigation awareness directly into the prompts or the process, making the optimization aware of noise from the start.
That's smart. Optimizing for the noisy reality. The overall trajectory seems pretty clear, doesn't it? It's this continuous push to integrate and refine how AI, especially these large language models, can become truly indispensable tools in quantum computing. It's about blending the best of what established quantum libraries like Cirq offer, the structure, the physics, with the sort of pattern-matching power and flexibility of modern AI, unlocking new possibilities.
So let's try and sum up our deep dive then. This project, it's revealed a really fascinating intersection. You have the structured, sometimes rigid world of quantum circuit design and simulation, meeting the flexible, powerful capabilities of modern AI.
Yeah, it stands as a really great example of how you can combine established tools like Cirq with these cutting-edge AI models like Gemini. It really highlights this powerful trend in science, doesn't it? This cross-pollination between
Accelerating discovery.
accelerating discovery, solving problems, opening up avenues that maybe just a few years ago seemed pretty much impossible.
Absolutely. And for you, our listener, maybe here's a final thought to chew on. Given how successful this in-context learning seems to be for something as niche, as complex as quantum circuit optimization, could this approach, teaching these big AI models complex tasks just by showing them a few tailored examples, could that become the go-to method? The rapid prototyping technique for specialized challenges across, well, maybe every scientific and engineering field. Something for you to mull over or maybe even explore on your own.